Hey guys, this is Saptarshi here and welcome to our YouTube channel. So if you are following our neural network playlist, I think you have already developed some idea about CNN. So today we want to discuss a very important CNN architecture called as LeNet5. Okay, so this was proposed by legends like Lecun, Joshua Begio and their team in late 1990s, right, around 1998. And why it is still relevant is because some of the ideas they proposed in this first established CNN architecture was quite landmark and changed the way neural network models were used for computer vision tasks. So this is the paper which has already around 30,000 citations. And if we just get little carried away and share some of the tidbits from this paper, please pardon us. So here is one of the tidbits to start. So they discussed about an equation, which establishes a relation between the testing set error, the training set error, model complexity, and the training size that we have available. Okay. So these are the notations. So E signifies the error, right? So you see that E test minus E train is K times H by P to the power alpha. K is a constant, alpha has a value between 0.5 to 1. So you can think that it is domain specific, right, or task specific. So what is H? H is measure of capacity of the machine or the model. So you can roughly say that this is the complexity of the machine, maybe measured in terms of parameters, right? And what is P? P is number of training example. So what we are trying to say, so ideally what do we want? We want that E test to actually mimic E train, right? So we want this to be 0. And for that, what we want this H to be a small number, right? So we want the model to be very simple, right? Less number of parameters. And we want P to be high. That is, we want large number of training examples, right? But that neural network has more parameters. So why we are trying to increase the parameters where it can actually increase the test error? So the answer lies in the optimization theory, right? So often, if you have a optimization function like this, so if this is your optimization function and this is one of the parameters that you have got, okay, so often we say that, or many of the algorithms, right, which are in heuristic nature or stochastic nature, they get stuck over here, right? They get stuck over here, which is called as local minima if we start somewhere from here and doesn't reach the global minima which we actually want to reach at or achieve, right? So then why we are trying to increase parameter. So here is something directly from the paper, okay, which states that if we actually increase the number of parameters, right, so the tendency to get stuck at the local minima is much lower. So this has been one of the major criticism of neural networks, that which was not known. So you see that it states the fact that local minima do not seem to be a problem for multi-layer neural network is somewhat of a theoretical mystery. Okay, and they stated why this is happening is because you are taking more number of parameters. Okay, and now we are coming to LeNet5, and again one of the tidbits directly from the paper, that the convolutional network combines three architectural ideas to ensure some degree of shift, scale, and distortion invariance, right? So we are dealing with computer vision problem. So here is a all right, but this A can be little bit tilted. Okay, so this can be somewhat like this. Okay, it can be of lesser size, right? Or it can appear at any position of the image. Okay, and this is something very uncommon to traditional machine learning, right? So one of the things this convolutional neural net wanted to achieve is this some degree of shift, scale, and distortion invariance. And what were the weapons to achieve it? Local receptive field. So if you remember that when the convolutional layers are being built, they don't look at the image at the same time, entire image at the same time. So this is called as local receptive field, which is which is how actually human vision also works. Okay, and also this place which is your local receptive field, you go on, take stride and take another local receptive field which is of the same size, right? And the weights they share are actually same, or the weights that are applied on them are actually same. So that's why it is called as shared weight. And you do a spatial or temporal subsampling, right? So in terms of your pooling, so you have already looked at convolution and pooling. So pooling is a layer which is doing your spatial subsampling, which is giving you this level of distortion invariances. So here's a quick look. So this is your input image. The first is you have a convolution layer and you have 6 filters, right? And actually your input image is 28 into 28, but you apply same padding. So you pad it to 32 into 32 and you get a 28 into 28 image based on all the filters. So 6 filters, 6 into 28 into 28. Next, you actually apply pooling, then again a convolution, again pooling, and finally a fully connected layer. So we will look at the layers, in more detail shortly. So the first layer is called as C1 convolution layer. So you always ignore the discussion about the input layer, right? And the input is 32 into 32 grayscale image. So the first convolution layer, okay, actually has 6 feature maps, right, or 6 filters, right? And you actually the filters has a size of 5 into 5, right, and a stride of 1. So basically as it is 32 minus 5 plus 1, so that's how you calculate the target size. So from 32 into 32 into 1, for one filter you get 28 into 28 into 1. For 6 filters you get 28 into 28 into 6. Okay, so this is your input image 32 into 32 into 1, and this is what you are getting, a 28 into 28 into 6 feature map or the convolution. So now what we are going to do is you are going to do a subsampling, spatial subsampling by pooling, and at that point, please look at this very carefully. At that point of time, the pooling that was applied was average pooling. Okay, so that was not max pooling that we use now, right? And if we use a stride of 2 and a filter size of 2 by 2, then actually the image gets reduced by the height also by half and the width also by half. So from a 28 into 28 into 6, so from 28 you get a 14, from this 28 you get a 14, and of course you have all these 6 filters still intact. Now you have another convolution layer, and in this convolution layer actually you have this 6 feature maps, okay, from the pooling layer, and now you are applying 16 filters. And there is a very interesting thing, okay. So ideally, as these are now 3D shapes, the convolution is also a 3D convolution. So it is a 2D convolution, but you go the entire depth as there are feature maps in the previous layer. So in this case, ideally, uh, if my filter or number of filters is 6 and I am taking a pooling of maybe or convolution of a size of 3 into 3, so I'll assume that it is a 3 into 3 into 6. Okay. Now here what happened is that not all the feature maps from this layer were used or were convolved in this layer. Okay, so this actually give the feature map. So this comes directly from the paper. So what this tells is that these 3 features were used. These 3 features were used to get the first feature map, or the first filter was applied on the first 3 feature map. The second filter was applied on the first, second, and third, or rather second, third, and fourth, and so on and so forth. Okay. So why this was done? So it turns out that of course it results into less number of parameters, and it kinds of breaks symmetry. So these feature maps that or these filters that we are using now do not look at all the feature maps from the previous layer symmetrically. Okay, so this can actually give you better discriminative features or different features. So that was one of the core ideas. Okay, and then you have another pooling layer, okay, which is again average pooling, and the idea is again very simple. So you have a 10 into 10 into 16 input, right? So it will be halved because the filter size is 2 into 2 and a stride of 2 is used. So the output size will be 5 into 5 into 16, right? So this is where your feature map thing is done, and we are moving now to the fully connected layer. So we have now 5 into 5 into 16, a layer like this, which will be flattened, and we will get a vector of size 400, right? 5 into 5 into 16, and that will connect to one hidden layer which has 120 neurons. So that was there in the original paper, and this is the fully connected layer. So the number of parameters will be very, very high here, 400 into 120, and then of course you can have parameters for bias, so it can be 400 into 120 plus 120. And then you had another hidden neuron, another hidden layer which has 84 neurons. Again, it is a fully connected layer, so number of parameters are high. And finally you have a output layer, and like we use softmax and we have as many nodes as there are classes. Here also the output layer had 10 nodes. Okay, so this actually completes the architectural points that a CNN has. Okay, now there was a difference in the loss function. So it was not a typical softmax function, but this is a radial basis function that was used. Okay, so let me quickly explain what this is. So W is the weight parameters for a class. So you have different weights coming to different weights that are coming to a particular output node, and you also have the input pattern, right? The input pattern that is there. And the idea is that the input parameter should be very close to the weight parameter, because the weight actually represents the class. Okay, so it is kind of, you can think it is kind of the centroid of a Gaussian distribution, and you do it for one class and then you sum it over all the classes. Okay, so this is how the loss function was different in case of your LeNet5 architecture. And this is a summary from this wonderful book by Aurelio Gueron. Okay, so you have this input where your size is 32 into 32, and it actually tells you the kernel size of each layer, right? So this is 5 into 5, 2 into 2, 5 into 5, 2 into 2, so on and so forth, right? And also the size here. So up to the convolution and pooling layer, you are calling this as maps, and then you are calling it as size, because now you have flattened it, right? And it also tells you the activation functions. So only one thing again I would like to draw your attention is the activation that we are using over here is RBF and not the softmax function. Okay, all right. Now let's look at some of the invariances that Lecun proposed or brought forward. Okay, so if you look at this particular image, so this first thing is showing translation variance or shift variance, right? So anywhere actually 4 comes, it can actually, anywhere actually 4 comes, it can actually identify it as a 4, because it is focusing on the structure. So it is looking at this line, it is looking at this line and how it is getting connected, right? So as there are different feature maps and focusing on different parts of the feature, it can still identify it as a 4. So this is where it is a translation. You can see it is rotation. This is where a scaling is happening, and this is what is called as squeezing. Okay, so all these cases it can actually identify. So that was one of the advantages of coming up with this kind of a layer in case of computer vision. Okay, this is some further examples where the first one actually talks about the stroke width variance. So you see the stroke width is getting increased, but it can still identify it as a 6. And here there is a lot of noise, right? So you can see this particular 3. Okay, there is a lot of noise that are introduced, but it can still identify the digit as a 3, right? So that kind of sums up what we had to discuss about LeNet5. And as I said that this is one of the very fundamental models of CNN. So we really need to appreciate the different architectural blocks. Okay, So thanks guys for watching this video. If you have any questions, comments, please give it in the comment section, and please do subscribe to your channel. Thanks you once again guys.